as a case study, we consider the Lorenz 84 atmospheric model, which is a toy model of climate, a very simple conceptual dynamical system. The outline of my talk, I start with a brief introduction, just to put the topic into context, how we define extreme events, and how we wish to predict these extreme events. Then I briefly introduce the Lorenz 84 model of global atmospheric circulation, the dynamical system that we analyze. And I also explain how we introduce a driving term in this model, which is to mimic higher dimensionality of a system or additional timescales, which can also affect the predictability. Then in the main part of my talk, I describe more in detail the prediction scheme and also the scoring scheme by which we evaluate predictability. And then I analyze how this prediction determines on several factors. First, the kind of variables, observables we look at to be able to determine whether an extreme event would occur. So the kind of composition of this precursory structure and also the size, how many variables we look at. And then in the second part, I give an analysis, basically a numerical case study, how the predictability depends on the prediction lead time and also the event size. And besides a scoring scheme, which is the ROC statistic, arguably a suitable one for this kind of prediction of rare extreme events. I also consider another measure of scale, the finite time Lyapunov exponents, which was proposed in the literature, and I compare the two. And in the end, I give a summary. So what is our problem? Very often we are presented with an observation in time. So we have a time series, and in the real world, systems are governed by deterministic processes. Many times they can be looked at as time continuous processes.
May I criticize something?
Yes.
In real world, time series is more spiky.
Yes, that's right. But but they are continuous.
Well, it's something we have to worry. Things like a rainfall.
Yeah, rainfall is an extreme case.
Yes,
Yeah, very extreme
that's
case.
right. So I cover part of our world.
Well, we have to be careful whether using a right toy for purpose.
Mm-hmm. Yeah, sure. So it's up to you in the end to decide whether this scheme is applicable
well,
to.
Well, you already decided to choose this one. Yeah. Anyway, keep going.
Okay. So surely there are observations which are at least similar to this kind of time series. So there is some use in here, and the way we define events in this context is threshold crossing. So there is this horizontal line, and if the signal is above, then we say that there is an extreme event or a strong event occurred. And looking instead of the continuous process, we discretize the problem in the sense that we only look at the apexes of the time series, so these upper turning points. And then the task is to predict whether the next apex would be beyond the threshold. And whether we can do this can be prompted by some properties of the time series. For example, if we look at return times of the time series, An example is shown here. So between two apexes that are crossing the threshold, we have some return time. So if we evaluate a distribution of this return time, then we might see exponential tail, which tells about the loss of correlations. But in the beginning, for low return times, this distribution might be non-exponential, and that's a sign of predictability. This example is for the Lorenz model itself, and we see that there are gaps in this distribution, and yeah, it's strongly non-exponential. So the model itself looks like this. I suppose many of you know this. It's an equation. It's a system of three equations written for globally averaged variables. X is the wind speed of the westerlies averaged over mid-latitudes, and Y and Z represent eddy activity in terms of the amplitudes of the two principal modes of the eddies. The equation itself expresses a balance between the kinetic energies in the winds and the heat transport, which is facilitated by the eddies. So we see that we have a conservative part of these equations in blue, which is nonlinear, and we have a linear dissipative part. And as we see, Y and Z do not have a prefactor, meaning that the equations are non-dimensionalized with respect to the eddy decay time, which is about 5 days. And then the red color shows the forcing of the system. In the autonomous system, these are constant forcing terms. F describes the solar forcing in the sense of the temperature difference between the equator and the pole, and the 1 in the other equation for the eddies describe an asymmetry between the two eddy modes, representing the continents.
What does conservative mean?
That,
Hamiltonian?
yes, yeah, it means that if there were no dissipative terms, the energy would be conserved. The energy in the sense of y squared, z squared plus x squared. So the total energy in the system, kinetic.
It conserves the energy, but it's not in Hamiltonian form. It's not a Hamiltonian system.
Is the blue part not Hamiltonian? I would think you could put it in that form.
Yes, probably. So this system wouldn't have an attractor because it's not dissipative, but there could be a sustained oscillatory motion.
The blue system?
Yes, yeah, which depends on the initial conditions. So there is not an attractor.
You would need the green terms for that and the red terms.
Yes, yeah. So, yeah, and obviously the larger the solar forcing, the more cold conditions are represented. So Lorenz took the value 8 for winter and 6 for summer. It's just a metaphor of the seasons. And this model is known to exhibit some rich dynamics.
Can you go one slide back?
Yeah.
Sorry. Do you know what the energy is for the blue part?
No.
I'm going to try to do it during
The sum of the squares.
Yeah. Sorry, I meant. I thought you meant the.
Or mathematical one? Does it correspond to real whatever energy from original system?
Of course.
I suppose so.
Yeah, it expresses a physical.
It does, and it probably will. Yes.
Okay.
Yeah,
You should trust Lorenz.
I don't say, but
I'm joking.
but it expresses a physical process. So yeah.
I don't know what physics means. This guy Lorenz.
So
X and Y. One is the kinetic
Yeah,
energy
the
and
other
the
the
available
potential.
potential energy of
As you-
baroclinic flow. This is a truncated system. The minimal truncated system of quasi-geostrophic equations.
That's right. So Lorenz didn't derive it from the equations apparently,
Okay, so
but
bottom line,
much later.
This came from quasi-geostrophics.
Yes, it can be derived by truncation and central metaphor reduction. Yes, so it's a highly idealized, highly simplified model. And due to the nonlinearities, we have chaotic solutions in it for higher values, typically higher values of the solar forcing. For the Lorentzian winter, we have a single-piece chaotic attractor, and for summer, we have a coexisting period 4 attractor and the period 1 attractor. So in this bifurcation diagram, all the coexisting attractors are represented, and so we have some regimes where we have even 3 or perhaps 4 coexisting solutions. So there is a rich dynamics in this system, but we will focus on the chaotic part because this is the less trivial one from the point of view of predictability. So just a further view on the chaotic winter attractor living in a 3-dimensional phase space x, y, z. Here we can see it in a front, side, and top view, and it looks space filling more or less. But if we make a Poincare section by this surface, represented by the black line at the z equals node plane, then we can much better resolve by the eye the fractality in 2D.
Front means YZ space.
Yes, sorry. So this is y, yeah, and that's z. So
Read.
yeah, sorry. The letters are very small. So yeah, and this is x that you rotate up here. It's a kind of engineering point of view on 3D space. And we have here some time series as well for the different components x, y, and z. You can see that the x variable has a longer typical time scheme as compared to the eddy variables. And also I plot here a further composed variable r, which has a similar time scale to x, the first one. And this composed variable is simply the total cyclonic activity, kind of radius of the trajectory in the YZ phase space or plane. And we also consider a driving of this system, as I said, to represent further timescales or higher dimensionality of the dynamical system. We introduce this driving through the solar forcing, which can be thought of physically as some modulation of the forcing through, let's say, weather conditions, cloud dynamics, or any other process that can alter the albedo, let's say, or orbital modulations. So this is just a metaphor for the higher dimensionality of a system. We choose to use a chaotic driving for F. So F has a mean part and a fluctuation, and this fluctuation term can be defined by some process of X tilde, which could be the first component of the classical Lorenz equation, for example. There is no physical meaning here, it's just we try out a chaotic process. And alternatively, we can also use a white noise driving for the process X. And I would point it out that we amended these equations by time scale term tau L to be able to vary the relative time scale of the classical system to the climate system that we consider the Lorenz 84.
Do you have reason for picking this up?
Sorry?
Why you take Lorenz 63?
Just as a try, just because it's chaotic. So it's a
It could be
concept.
anything.
Yeah, it could be anything. It's just a concept.
You usually choose the driving to change on the timescale faster than the natural variability or slower?
Yeah, good question. So we do both. Yes. So in this study, I will.
The stupid question would be, what would happen if you couple with same system with different timescale? Is it stupid exercise?
No, it's not. We tried to couple with Rössler system, which also has actually a similar spectral character that the Rössler system has peaks in the spectrum. So I think it would be a similar exercise to that. But yeah, for this study, we chose the Lorenz model, which has not a peak in the frequency spectrum, but the time scale is characterized by this crossover, which corresponds to a frequency that is the frequency of oscillations on one wing of the butterfly attractor. However, when we want to choose the time scale, this tau L, for the Lorenz system so that it's comparable to the climate system, which is about 4 time units, that is 20 days in real time. We do this by looking at this resonance effect. So in an earlier study, we varied the timescale of the Lorenz, and we looked at the response in terms of the maximal extreme events of the climate model and also the kurtosis of the extreme events. And we saw this maximal enhancement at a certain time scale of the driving. So we said that at this time scale should then correspond to the climate model. So this is a time scale when the time scale of the forcing is comparable to the original model. And this is slightly different from this crossover frequency. In fact, about 2 times that of frequency. So we use tau prime 1 for one experiment, but we also use this tau prime 4 value, meaning that the driving is 4 times faster than the original system. So back to the problem of prediction. Here is example time series, and we would like to predict whether some apex would cross the threshold. We define event variable high I at the time instant ti, and say that it's 1 if there is a threshold crossing and 0 otherwise. So for example, for this peak in between, at 0. And then at every time instant t I minus 1, we make a prediction for chi, which we just denote by a hat. So how do we make this prediction, this high I hat? We try to assess the probability based on our time series data, how likely it is that we have an extreme event. And the way we can do that is that we pick out the time instance when the extreme event occurred, and then we look what happened before. And then we characterize this preliminary event by so-called a posteriori probability function. So
Can you make it formal, or do you just say in words?
yes. So on this slide, we have the posteriori probability function, which is a conditional probability. So we look when an event happened, that's our condition, and we compose the probability of that variable or structure of variable that we monitor. in order to make a prediction. And when this probability is high, then we say that it's quite likely that an event would happen. But still, we have to decide whether we issue an alarm or not, that we think that an event would happen. So it's a prediction in a yes-no sense. The high I variable is a binary variable. So this is one strategy to make a prediction, but we can also have a slightly different strategy where
I don't get it. Chi is somehow is you at time t over threshold or not?
Yes, chi is a binary variable, it takes 0 or 1 value, and it's 1 if x is over the threshold. So so for this time instant we have chi 1.
You want to predict how high you are above the threshold?
No, I don't. That's not our interest. So it's a yes/no
But
event.
I don't understand your conditional probability, because the conditional probability of x conditioned on chi, but x is
So x is a continuous variable. That's the precursor variable that we monitor. It can take real values, but high takes only 0 or 1.
How you will be conditioned on the fact that you're over the threshold.
But this is the definition of high, the value. So it's conditioned that we are over the threshold, but it's a one-to-one correspondence. The value of high 1 when the time series is over the threshold. It's 0 if it's not. So there is a one-to-one correspondence. In a way, there is no condition here.
This is but x, you said, so this is basically p of x is basically if you have the whole probability distribution of your variables and you cut just above the threshold, that's what you obtain, is it? Because this I read is the probability distribution of x, assuming that I am above threshold.
Yes. So it's
I'm cutting, I'm removing everything below threshold, I'm renormalizing, and I have the new probability distribution.
Yeah, that's correct.
So
Yeah.
it's the over threshold event.
Yeah. So it's a subset of x's. Frequency. Which one? Sorry.
You got the probability, but you're counting frequency.
Which one is the frequency
Everything.
count? Yes. The probability is a kind of frequency or relative frequency. Yeah.
Well, otherwise it's confusing because x is time series, and then
Yeah. The probability is a kind of frequency measure, relative frequency. How often that.
Valerio said.
Okay, so this is one strategy to predict the extremes based on the
As
posterior.
Valerio said, this is nothing other than renormalization. Instead of taking whole range for x, you just focus on x larger than threshold. Is that the point?
Yes.
Okay.
Yeah. Or we can have a different point of view, that we don't throw out any data that when an event didn't occur, but for every time instant, for every value of x, we assess how likely it is for an event to occur. So as you see, the difference between the posterior probability and the likelihood is just a change of the conditional, the variables which is conditioned on which. And because of that, according to the Bayes theorem, we have that the likelihood is the posterior probability normalized by the parent distribution of the variable or the precursory structure. And this allows to right away say that probably the likelihood will perform much better because P is always smaller than 1. So while some events look low probability from the posterior probabilities point of view, it might have a high likelihood anyway.
I guess we're missing something.
Yes.
If this PP is just matter of renormalizing original probability, this likelihood will be simple step function.
Yes.
Is
Yeah.
it right?
That's what I was thinking the same, so I'm not understanding.
It takes, the likelihood takes values between 0 and 1.
So it's just 0 and 1.
Yes. Takes values between. It can be anything between 0 and 1.
No, why that happens? If PP is just renormalizing Px, then this is constant, and PP is actually the proportion to P above threshold, and if below threshold, PP is 0 by definition. So by dividing PP by PP, you get 0 below threshold. If chi is not equal 1, you get probability 0. And if you get condition chi equal 1, you get certain constant.
Yeah, but this PP doesn't have the same shape as P.
That's what we don't understand.
Well, so it doesn't have the same shape because the way you construct this posterior probability is that you don't look at all these x's, all individual, but you throw away all those that are not followed by a threshold access. So for example, we only keep this one, this one, this one, this one,
You only look
and
at peaks.
this one, this one, this one.
Oh, you're looking.
Yeah. For example, we don't keep
only
this
looking at
one
extremes.
because it's not followed by an extreme event. We don't keep this one. So we construct a distribution only by x's which are followed by an extreme, but not those that are not followed. So it alters, it gives a totally different shape to the parent distribution.
Yes. Instead of P of x is the distribution of all events.
Yes.
But by event, do you mean only the maxima or all the distribution?
Only the peaks, these turning points, only the apexes.
Oh, so you're only considering the, so you take this
Only the
and you
apexes.
consider only the apexes.
Yes. Yeah.
And you do it at different times.
Yes.
X and chi live at a different time.
They correspond to the same time. So
You're looking at chi and
yeah. So here we have xi and also chi I.
Yes, but in your conditional probability, you take the xi for one time because you want then to see that at x chi I plus 1, you will be above.
Yeah,
so
yeah.
The x is at I and the chi is at I plus 1 because you want to predict.
Yes. So this chi I we base on xi minus 1.
Okay. We have to read it.
Sorry, it's not written here. But okay. So yeah, chi I hat is determined by x minus 1, I minus 1. Yeah, or other previous instances as well.
It also depends on time step.
Um,
This I minus 1 means.
the time step?
Well, what is Ti here?
Ti are the instances of the apexes when it occurs.
Okay, Ti is particular instant, and how you define Ti minus 1 relative to Ti?
So if this is Ti, then this is Ti minus 1.
Okay, you look at okay, that's the way to define it. Yeah, okay. Well, you said at the beginning, return time, whatever. That's the idea.
Fine. So yeah, we have two strategies to issue predictions. by characterizing the probability or the likelihood of an event to occur. And so the likelihood is expected to work better because it's normalized by the parent distribution. And we will soon see how the distributions differ. But before that, I will describe how this kind of prediction is assessed. So this is done in terms of two measures, the hit rate and the false alarm rates. So the hit rate measures the true positives when we were correctly predicting an event, normalized with all the events. And the false alarm rate is determined in a similar spirit. So we count how many times we were wrong in predicting an event relative to the number of all non-events. So this kind of normalization makes these quantities a suitable one for predicting quite rare events. This can be contrasted against other skill scores like the Brier or ignorance score, which are kind of dysfunctional for this kind of prediction task. But these hit rates and false alarm rates depend on the threshold that we impose on the probability or the likelihood. So we compose for each value of the precursory structure how likely the event would occur, but whether we issue an alarm in a yes-no sense, we have to define a threshold. So if the likelihood is over 0.7, then we issue an alarm, but not below. But what exactly this threshold is up to us. And then we can actually vary this threshold in the whole range. And then with that, we can plot this so-called receiver operating characteristic curve, just the hit rate against the false alarm rate, where the curve is parameterized by this threshold on the probability. And then when there is a scale of prediction, we have this kind of convex function. The no scale would correspond to a diagonal line. So that's just random prediction. It could be based on not a probability function, but a coin tossing. And so the meaning of this curve is that here in the 0, 0 corner means that we don't make many mistakes. False alarm rate is small, but we also don't get many events. We miss a lot of events. So this is a very safe game. So we don't issue a lot of predictions. The threshold and the probability is very high. But if we are lowering our threshold a lot, then we can get most of the events, but we also generate a lot of false alarms. So obviously we should somehow stay in between. And the ideal situation is this 0, 1 corner. So to have a summary statistics of this ROC curve or a summary measure, we can take, for example, the area under the ROC curve, but I choose to do rather measure the distance between this ideal corner and the curve. And let's try this scheme out. Yes, because I didn't label it, but this one, for example, corresponds to the likelihood, and the other one corresponds to the posterior probability density. And I assess here both. So this is the likelihood and posterior probability functions in terms of the precursory variable. So structure in quotation mark because it's just a single variable at the moment. And this is done for the undriven or autonomous Lorenz 84 with these parameters. And we can see that the likelihood function is much more fat in this sense than the posterior probability because it's normalized by the parent distribution. So the parent distribution also has similar peaks around here, but when this function is normalized, the low values of the parent distribution result in a higher value in the likelihood. So it picks up more events, especially overall, these values are not very frequent, but when we normalize the posterior probability with the parent distribution, we actually find out that even for this single variable, precursory variable, we can predict with perfect, with certainty, at least a few events. So this cannot be predicted with certainty, but we can run a threshold on our probabilities and draw out these curves, and we see that the one with the likelihood is always above the posterior probability.
Yeah, getting back, well, it's saying here, well, could you go back?
Yeah.
So how much detail we have to stress on this? Are these two peaks are meaningful?
These ones.
Yeah, and then there's some tiny peaks where the left peak got...
This one or this?
Well, the highest peak got the second peak just next.
Yes.
No, really just next.
I see, this one, yes.
Yeah. Is it meaningful?
Well, it's meaningful in the sense that for these values of the variable, it's likely that an event would occur. So that's the meaning.
The question is this time series long enough to get stable statistics?
Yeah, thanks. Yeah, that's right. So we generated a very long trajectory. So these kind of hairy, non-smooth features of the distribution are real. So actually, you can see that we use the bin size, which generated this kind of box count, or for the so we have a lot of points in the boxes.
And this is single one.
Single one?
Single one.
Yes, a single one.
Does it depend on initial condition? Because this is funny, strange after.
Yes, it does depend. It does depend. Of course, there is some statistical error in it, but for this length of the.
Depending on your initial condition.
Yes, it would, but it's so small that there is no point to plot an error bar because it's so tiny that you wouldn't notice a difference. Yeah, the statistics is very, very robust here. No dependence, no significant dependence on initial conditions. Yeah, so the same goes for the driven system. And we see that in this case, the distributions are much smoother. So the previous distributions was hairy because of this fractality of the attractor. But these main features are retained, the two peaks and the more fatness of the likelihood. And if you look at the rock curves, we can see that the one for the likelihood is above always the one for the posterior probability. And we can also see in the background with gray the curves for the undriven system. And we would expect, we satisfy our expectation that the driven system is less predictable than the undriven one. So more information is lost. And then we can size up our or increase the size of the precursory structure. So we look at not only the previous event, but the previous two or values of the variable, and then our distribution functions are over this plane of these delay variables, and we see that the color scheme is blue for 1 and dark red for, sorry, blue for 0 and dark red for 1. So in fact, where you see red, the likelihood is almost 1. Only here we have a slightly less or significantly less likelihood, which probably is to do with the folding of the plane where these events, these apexes, are situated in the phase space. So in the phase space we have a plane of these apexes, and when we transform this the variables from the original x, y, z to these delay ones, then this plane is probably folded, so there is some overlap, and that we can see in this scatter plot. So some parts of it are nicely fractal, but elsewhere it is compromised, and we can, looking at it, we can imagine how this folds. For the
threshold? What's your choice of threshold?
it is the same, so I didn't change. The threshold is still 1.8 on x. And this is what we get for the ROC statistics. So compared to using only one variable, the predictability is much better. By the way, so for the posteriori, you see only blue, but in fact there is a small red dot there, which corresponds to a very, very high peak. Not a singular, but it's a very spiky distribution. And you can pick that peak up more from the driven system, where the scatter plot is just a blurred version of the previous one. And same way we can construct likelihood and posterior probability, and we can see that the likelihood picks up a lot more event than the posteriori one. Of course, these events are rare, but still predictable. So we always have the ROC curve for the likelihood above the one for the posteriori. And again, compared to the undriven system, the driven one is less predictable. So to do with this folding of the Poincare section, let's try to eliminate this problem. And in this particular model, it's easy because we know the Poincare section. So if you look at the apexes of x, that's a kind of Poincare section because that means that at the turning point, x naught is just 0. So we can get this surface as the right-hand side of the equation. And as we see, it has y squared, z squared, and x. So it basically is just the equation of a circle whose radius is given by x. So that's a cone in the three-dimensional space. So we have a conic plane on which crosses the attractor, and then we have this nice fractal structure. And we can unfold this cone by introducing this new variable phi, which just traces around the surface of this cone, and we can represent that in a plane. So what we get is a clear fractal structure which is nowhere compromised. So there are no overlaps in this space. And correspondingly, the likelihood is almost 1 or 0, or very closely. So there are never foldings. If it's not 1, that's only to do with the coarse graining, because we have a finite time series, so we have to choose a finite box size to construct these distributions. And for the posterior probability, again, we have a peak here. And the predictability is very nice, so we can hardly see in this scaling of the window the error in prediction. And if we again introduce some driving, then there is a slightly more blurring. This shows up finally where that peak was in the undriven system, and then we have a slightly poorer predictability. So here's this table that summarizes the skill, looking at different versions of the system, the undriven one, the driven by the Lorenz, slower one and the faster one, and also driven by white noise. And I have these values here for the posterior probabilities and the likelihood as well. And the values themselves are this distance from the ideal corner. I didn't write it here. But we see this general trend that the bigger the precursory structure, the better the predictability. And for all of these situations, when we manage to normally, properly unfold the phase space, then we have the best prediction for all cases. On the other hand, if we look at the single precursory variable, we see that the white noise-driven system is more predictable than the undriven system. And that was surprising for me in the beginning, and I thought it may be because the X variable is a kind of red noise process, so it's not smooth. So I thought maybe my algorithm picks up not only these local maxima of the time series, but also these small wiggles. And then so I tried to smooth the time series, which eliminated these close returns of a maximum. But there is not much change for the single variable. So a very slight change, and it still looks to be better predictable than the undriven system. So my second thought was that this must be because the attractor geometry is such that the weight of the attractor is not situated in the folded areas as much as in the undriven case. And when we include more variables, we better unfold the phase space, then the undriven system wins over the driven one. And there is another kind of peculiarity in this data set, that I consider different phase timescales of the forcing for the Lorenz 63. And when I used 3 delay variables, I hoped that the slower Lorenz will be better predictable, but this is not the case. So here we have 1, 4, 3, 4, 1, 3, 5, 0. So the lower value is better predictable. And then we must conclude from this that the intrinsic properties of the system, like the instability of the trajectories or the shape of the attractor, are involved in a different manner depending on the precursory structure. And and these precursory structures seems to not favor this slow system as much as this one, so that even if we can pick up more information of this by more precursory variables, the kind of observable is still not as good for this one. So I did the same analysis for another variable, the cyclonic activity, and still the situation is the same. The slower Lorenz is better, is not as well predictable than the fast one, but otherwise here the white noise driven system is not as well predictable as the undriven one, the way we would expect. So the geometry of the attractor does not play a significant role in this case. So this is a summary of what I have just described based on these tables. So we have a number of factors what determines prediction skill, the size of the precursory structure, type of observables, intrinsic characteristics, and these three are somehow grouped together. So it's difficult to examine the effect of just changing the size of the precursory structure. These intrinsic characteristics will be also involved. So, but on the other hand, the likelihood, or whether we use the likelihood or the posterior probability function, we know that it's always better to use the likelihood. All right, so in the second part, yes, I cut it short. There are two other factors that I examined how the predictability depends on. One is the prediction lead time, and the other is the size of the event. So first of all, the prediction lead time. In the previous case, we looked at discrete times of the system, so we can't really change the prediction lead time, or only in a discrete manner. But if you don't concentrate on the apexes only, but any value of the original variables can be considered to the precursory structure, then the prediction lead time can be continuously varied. So as a precursory structure, we look at the all x, y, z coordinates of the original Lorenz system, and we try to predict not the apex, whether it's above the threshold or not, but whether the trajectory crosses the threshold in a certain given time, delta t time window. And then this time window and the threshold will define an event volume in phase space. So we want to predict whether from any point in phase space we get into this event volume. And what we get for the undriven and the noise-driven system, depending on the prediction lead time, that the predictability, of course, deters as the prediction lead time is longer, but in a non-monotonic manner. So we see that there is sometimes a return of skill. It's worth to predict even more ahead because the skill will be better. And this kind of property is preserved to a certain degree even when the system is noisy. And there is another skill measure possible other than the distance from this ideal corner. Sterk, Holland, and co-workers propose in this paper to look at the finite time Lyapunov exponents. So evaluate that what is the average instability of the trajectories from this event volume to the point where we would like to make this prediction. So the finite time Lyapunov exponents over period of the prediction lead time. I guess everyone knows the definition of the finite time Lyapunov exponent. So what we get for the two measures are these. So here we plot the prediction skill on the vertical as a function of the prediction lead time and the threshold. And we consider these two prediction skills. And what we see is that the dependence on the event size is not monotonic. So there are times when stronger events are harder to predict, but there are other times where stronger events are easier to predict. But this thing is not picked up by the finite time Lyapunov exponent. And these two diagrams are for the undriven system, yes, here. And I also did that for the white noise driven system. So there are much broader features in here. But one can pick up these anomalies or seemingly errors that the d is nearly 1. And the maximum value of d should be square root of 2 over 2. So when we just predict randomly, we should be on the diagonal of this in this rectangle, whose distance from the corner is square root of 2 over 2.7. So this reveals that the rockers don't extend to the corner of the box, and that's to do with a wrong or unoptimal choice of the box for coarse graining. And in fact, I checked that the predictability depends in a simple manner on the coarse graining. There is a single maximum, so I numerically try to find a maximum. Obviously, it would be better if I could just pick by theory, but that's yet to be done. So finally, the result is this. So the situations where stronger events are less predictable disappeared. So almost always, stronger events are more predictable. In the driven case, there is something to the contrary of this, but I'm not sure if it's just numerics or a real thing. It has to be looked at. So just a summary appending that previous table. Basically, I just said it. And as an outlook, it would be good if we could somehow tell why the finite time Lyapunov exponents cannot pick up the same features as the ROC statistics. So we need a theory to relate these intrinsic properties of the system to the prediction skill. And then we would like to find more efficient methods or mechanically applicable methods to pick the right observe precursory structures, which are relatively slow, so that the numerics wouldn't be too much, but would yield a much better skill. And yeah, we can look for better advanced optimization schemes, not just a uniform box size, etc. So that's outlook for future work. And, thanks very much for the attention.
Thanks, Tomasz. So I guess we have time for just a short comment or questions. Dimitri?
Well, I got two.
Okay.
One
Okay.
very, very simple.
Well, you have a bonus, because you asked many questions, so you have a bonus of one question. That's why.
Okay. Well, key question is, imagine I give you a very, very long precipitation time series. Can you do the same?
Yes.
It will be useful. Would you do it?
Yeah, I'm quite confident that this is a very generally applicable method.
No, I will find the precipitation time series for you.
Okay.
You just have to tell me how long it must be.
Okay. Yes.
And then give it to you and wait for 3 months. Whatever.
That's hopefully enough.
What do you mean by very long? I mean,
Well, because you have to take a statistic.
yeah, but how many?
Well, how long
many
is?
events do you need?
Yeah. How many points you need?
It doesn't matter. I mean, that depending on the number of points, there is an optimal bin size that you have to use. So the prediction won't be worse than randomly predicting stuff. So the longer the time series you have, longer data, the better your prediction skill. And what is this function? How the prediction skill increases with data size? I'm not sure, but it is expected.
Okay, so I think we stop here. Thanks again.
Thank you.
Please.